going to talk about the concept of something called virtual functions. These are key to enabling our ability to create heterogeneous collections. In other words, collections of things that are not identical, which has been a restriction for us for not only the built-in collection types like arrays and and then being able to create linked lists and all that, but we've always had to create homogeneous collections where everything had to be of the same type and the same size. This is going to allow us to create collections of things that are not exactly the same, but that are related. In other words, they are part of an inheritance relationship or a class, subclass, or subtype type relationship. Now, obviously, the collections that we create of these will not be hard collections, meaning they won't be the actual size of the individual objects because there'll be different sizes. So it's going to have to be collections of pointers to these things. Where the pointer is of the base class type, that's going to be important. In other words, we want to use pointers that are of the common linkage between these different classes, and then at runtime we'll decide which functions to use based on looking at each pointer, what it points to, and seeing what the actual type is of that thing it points to. This is part of this polymorphic behavior that we've been discussing and we've been leading up to this entire semester. We've talked about this concept of, gosh, wouldn't it be nice if we could have heterogeneous collections? And now we're finally going to get to the point where we can create those. Now, before we look at exactly how to do that, there's a couple things we need to review. One is remembering about the constructor and destructor order, which we've talked about previously, that as we build an inheritance hierarchy, if we construct an object of a particular type, the first thing that gets constructed is whatever the root class is, or the most distant base class, if you will. And then we add the layers on top of that until we have the object created from all the different layers that are part of its inheritance chain, if you will. Now, we haven't created any that were really long up to this point. We had maybe a parent and a grandparent, but the concept is the same even if we extend that farther and farther. And then when we destroy the object, and we call the destructors for each of these different types and subtypes, remember they're called from the top down. In other words, we strip off the outermost layer, then the next layer, the next layer, until we get to that core, if you will. And we've discussed this previously. So in this example, class base has a constructor and a destructor that simply print messages so we can see what's going on. And then there's a derived 1 and a derived 2, so we have basically a parent and grandparent. Derived 2 being the outermost shell and the one that we're going to actually use. So we see in the main example shown here that we created an instance of derived 2 called D. And in the process of doing that, each of the constructors will fire, and then given that that's the only thing in main, the destructors will fire right after that. So we would see output that looks something like what's shown here. We call the base class constructor, then derived 1, then derived 2, so we've created the layered object, and then when the destructor is called, we destroy the object in exactly the opposite order, shaving away the layers until we get to the core and then getting rid of it. Okay, these two just reminders give us the foundation, then we need to start talking about this concept of virtual functions. Now, virtual functions require some different work by the compiler and then therefore the runtime environment. So in normal C++, when we're dealing with non-virtual functions, if you will, the correct function definition to call, even if it's overloaded, is defined at compile time. In other words, based on the signature of the function and its class membership, we know which one to use, and we decide at compile time which one to use and construct the ultimately executable machine code based on that knowledge. And we call that function, or we call that process, if you will, static binding. In other words, the functions that need to be called to match a particular function name are all done statically at compile time. So by the time the code runs, we know exactly what we're doing. So in the runtime world, everything is pre-scripted, if you want to think about it that way. In the case of virtual functions, what we need to be able to do is we want to defer that matching for certain functions, only those that need to be this way because of the hierarchy and because of the heterogeneous nature of our collection. So it won't be for every function, But for certain functions, we need to defer that decision about which one to use until runtime, because we're not going to know until runtime, because we've got a bunch of pointers to objects that were created on the fly dynamically, which one to use. We call this dynamic binding. And although it doesn't discuss it in this particular slide deck, the way this happens essentially is the compiler builds a little lookup table where the function call would normally be. And the lookup table basically says, okay, if the pointer points to an object of the base class type, use the print function from the base class. If it's of the first child of the base class, call that class 1, then use the class 1 print function. And if it's the outermost layer, class 2, like in our previous example, then use the class 2 print function. But it can't know until runtime because it doesn't know what that pointer is going to point to. We define and declare these certain functions that we need to have this capability with the keyword virtual, just like we did with friend in a previous lecture. So we put the keyword virtual in front of it, and that tells the compiler to use dynamic binding. Now, your first blush reaction might be, well, why don't I just mark them all virtual? And then I have this capability with all of them, even if they don't have different versions of the same function, like print, for example, in all the different levels. Maybe there's only one at the base class level, but I'll declare them all virtual. The reason you want to avoid that is because the creating of this lookup table and all this extra work that defers things until runtime obviously takes a performance hit on the program. Instead of everything being well scripted so I can just run through it, I have to, in the middle of running, have to make decisions. So we don't want to do this any more than we absolutely have to. It's a really neat feature and it's really useful, but we don't necessarily want to do it when the table's only going to have one entry in it anyway. If there's only one function that could possibly be called, then why would I build a lookup table and defer till runtime deciding which one to call when there's only one choice? So certainly don't want to do this if I don't absolutely have to. So again, the virtual keyword indicates to the compiler that the definition of the function to use should be based on the type of the object that the reference or pointer refers to and not the type that it's declared as. Because all the pointers are going to be declared as the base class type. That's the most common thing. Okay. So it's a function that you're going to redefine for other derived classes, and then you want to be sure you call the right one. So this is a good example of the polymorphic behavior of C++. And a class that has or inherits a virtual function is called a polymorphic class. So we use the prefix virtual. This redefines a virtual member function in derived classes. It's a type of overriding. It's similar to overloading, but we're overriding it. In other words, overloading says, hey, within the same class, I've got 2 or 3 different versions of this same function, but I want to differentiate between based on their argument list, the types or numbers of arguments. Here we're saying something similar, except it's between classes, not within the same class. So that's a good way to distinguish overloading from overriding. Overloading is repeating the name of a function within the same class, but with different arguments or different signature. Overriding is repeating the exact same signature, but in different classes. So that's the difference. Overriding, the signatures all have to be the same. They're just declared in different class hierarchies and different levels of the class, so in an inherited class. Whereas overloading, the signatures have to be different. And overriding, the class that it's a member of has to be different. And that's a good test question, too. You'll probably see that on an exam. So they have to have the same name and the same parameter list, whereas in the overloading, they have to have the same name but different parameter lists. Once I've declared something as virtual as some level in the hierarchy, like at the base or wherever it is, I don't have to use the keyword virtual again. It doesn't hurt if you do. My own personal choice is I usually repeat the virtual keyword. That just helps me remember as I go from one class to the next which ones are exhibiting this polymorphic behavior, which ones are the virtual ones. It doesn't hurt if the keyword's there again, even if I declared it at a higher level, if you will, in the hierarchy tree. The return types can be different, but that's the only thing that can be different. Otherwise, the signature has to be the same. So if I put different parameter lists, then that's not an overridden virtual function. So sometimes those actually become hidden methods and they can't be called. So I want to be careful about doing that as well. So let's look at an example here. Here's a class A, which is going to ultimately be our base class. And it has a virtual void function f. So f prints out a message, and we've declared it virtual, and has a signature with no arguments. And then class B, which is derived from public A, also creates an f, but it takes an int. So that's not really overridden because it has a different signature. And then class C creates a function f, which does match the same signature as the one in class A, so this would override the one in class A. Now, what effect does that have on us actually using it? So let's look at an example. We create an instance of class B and an instance of class C. So one that's the outermost child or grandchild of class A. And then we create a couple of pointers, because remember, to invoke the whole virtual function concept, the runtime concept, we have to be using pointers. So pointer 1 is a reference to, has the address of the B object in it, and pointer 2 has the address of the C object in it. What would happen if I said b.f? Well, that's a good question. It would, first of all, say there is no f function in class B, so which one would it use? Well, it would use the one in class A. That's currently commented out, so we don't see that output. Or would it? I'll let you think about that for a second while I finish the rest of this. So when we use the pointer A1, the first pointer, which has the address of B, and we point to F, which one's it going to use? Well, in this case, because we're looking at it through the pointer, it's going to start at the outermost shell, which in the case of this particular pointer is a B class, and say, is there a function F? No. Well, then it's going to go to the next layer and say, is there a function F? Yes, it's the one in A, so it'll use that one. What about the second pointer, pointer 2? We call this function F, so we go to the object, which is of type C now, and we look at the outermost layer and say, is there a function F with no parameters, etc.? Yes, so we use that one. We don't go on in and look for one. So we search from the outermost layer as appropriate, however it's declared, towards the core, looking for a function that matches that signature. And of course, there's a lookup table to help us find those. Now, let's go back to the commented outline b.f. Now there I'm not using the pointer, so I'm not invoking the virtual function capability. I'm not invoking the runtime capability. So if that comment was taken out, the compiler would try to match this function. So it would look for a function f with no arguments. And would it find one in B? No. And because I'm not doing this at runtime but at compile time, it says, sorry, no function. So I would get a syntax error from that particular line of code, which is why it's commented out here. So it would not get me to any usable function because it did not match the signature of the one that was in the B class, and we're not using the virtual function mechanism using the pointers to invoke the runtime decision-making process. This implies a compile time decision-making process. So I also can't call it with b::f because that hides another function. And again, B didn't have one. So it's not overloading because it doesn't have the same signature. So why is this important? Well, in a lot of cases, we create hierarchies where we want an operation to occur that semantically or philosophically means the same thing, but has different actions involved. As in this example, if we created a hierarchy of geometric shapes, at some point I'm going to want to draw those shapes. In this case, the base class is line, and then we have rectangle and square and circle and ellipse, etc. Drawing each one of those is not exactly the same operation. If we were thinking about moving a pin on a plotter, that would not be the same sequence of steps to do each one of those, but they all semantically and philosophically do the same thing. They render that particular shape on a screen or a piece of paper or whatever the case may be. So this is why we want this capability, so that we don't have to create separate functions called draw rect and draw square and draw circle and draw ellipse. We can, based on how a particular object was created and the layers that were included in it, we can draw appropriately. For example, in the rectangle and the square, they're really made up of a bunch of lines. So the draw may actually be doing the line draw. We just have to do it more than once. Whereas in the circle and ellipse, we're really not drawing lines. There's no lines involved. So the drawing mechanism may be very different. But philosophically, the concept of draw is the same regardless of which of these shapes we may be drawing. Okay? This also may help us enforce a software design. In other words, developers have to define their own implementation for a particular type of thing, but there's a common interface for it. Like, we might create a class called imaging device, and then there's different kinds of imaging devices like a webcam or FireWire interface or a disk image or a movie. And so the frames have to be acquired differently, but there's a uniform interface of how I go about building it. We can also enforce this software design concept using something called a pure virtual function. And we'll see that in the next couple slides in the form of a discussion and an example. The idea of a pure virtual function is a virtual function that has no definition. In other words, nowhere in it is there a set of curly brackets with some code. It's simply a prototype only. And its pure virtual function is usually provided in the base class, and what it does is it says, here's the definition of a particular function and what it should do and what its arguments should look like, what its signature should look like. But in the particular base class, it's not going to do anything. It's kind of like if our base class was shape. Well, how do you draw a shape? Well, I don't know what shape it is, but I can still define the draw function and say, everybody who's going to derive from me that's going to be a more specific type of shape is going to have to provide a draw function. That's a required element of your design. In Java, they call these abstract classes. So you can't create an object of that particular type if it's got a pure virtual function. So I couldn't create an instance of just shape by itself because it has no physical manifestation. But I could use shape as a base class and derive circles and squares and all the other kinds of shapes from it. And then they could provide a draw function that actually does something. So I'm enforcing a design. In a lot of ways, this is how, for example, operating system manufacturers might specify to, let's say printer manufacturers like HP and Epson, how do you interface a printer to Windows? Well, we'll provide you with a class that defines the interface and all the functions that are necessary that Windows expects to be there in order to interact with a printer, but we're not going to provide the code for them because the code for an HP printer to make it do whatever it's going to do may be different than the code that Epson writes for their printers to print a document or draw or do a photo or whatever the case may be. So the operating system manufacturers say, this is the features you have to provide, and this is what each function has to do, but we're only going to provide you with prototypes. In other words, we're going to call functions that look like this and have these arguments. You need to provide the specific code to do this particular operation for your printer, whoever you may be. And so we're basically defining an interface that doesn't have an implementation until the particular developer, in this case the printer manufacturers, define how that interface is implemented for their particular device. So let's look at an example here. It's very similar to our previous example, not exactly the same, but pretty close. So in class A, we have a function f, which is declared as virtual, but you notice there's no curly brackets and no code. Before we had a print statement. This one just says equal 0. That's kind of like defining the function address to be null, if you will. That's a pure virtual definition. So this says that class A has a pure virtual function, so I can never create an instance of class A. Although I can create pointers of that type, I can't create an instance of class A, an object of that type. But I expect that anyone who derives from class A, any children of class A, if you will, or subclasses, should provide a function f with no arguments that returns void. And as we can see, class B does so. And it prints out a message in this case just to illustrate the usage. And then class C, in this case, also does that, and it's derived from class B. Now, class C would not necessarily have to. It would still be instantiable, if you will, because class B did, and that would be part of the layer, if you will. But in this case, class C also has one, which would override the one in class B if the object is of type class C. Now let's look at that in usage. So here is that basically that same main code that we looked at previously, except without the commented outline. So it says create D objects and C objects, and create pointers to both of them, and then call F. So using pointer 1, which is of type, the pointer is of type A, but the instantiation is of type B, we'd call the F function in B, and using pointer 2, we'd call the F function in C, and we get the appropriate output as shown here. So this allows us to define an interface class that has one or more of these pure virtual functions, which then makes that whole class an abstract class, where we can define the interface without having to provide any dummy code, if you will. So there's another example using this imaging device example we were talking about. So here's a base class, if you will. Type imaging device, has some data that we need, like buffers and width and height and stuff. And then it's got a constructor. Those can't be virtual. You can have virtual destructors, though, and we'll talk more about that here in a second. And it's got some other virtual functions for initializing the device, getting an image, uninitializing the device, saving an image. These would be things that would be unique to a particular device, whether it be a camera of some type or some other kind of image capture, maybe a FLIR, a forward-looking infrared radar device. They would all have different initializations, different ways to get and save images, different ways to uninitialize the device, but they need to have all those operations. So here's what we define basically as a suite of operations that any imaging device needs to have. It's just that this base class doesn't have any of them because it's not for a particular kind of imaging device. It's basically a generic wrapper for all imaging devices. Then we could create, for example, a USB device from that had its own constructor and virtual destructor, and then it had its own instances of these 4 functions, and there's some code in there. We have dots there, but the fact that there's curly brackets indicates that there is real code. Those are real usable functions. So those we would then be able to create an instance of a USB device, for example. Now, I said we'd talk about the purpose of those virtual destructors. The purpose for virtual destructors and making them part of this runtime decision making is, in some cases, our classes, whether it be at the base class level or at the higher levels, may have dynamically allocated data. Remember, I'm using a pointer of the base class type, like class A in the first example or class imaging device in the second example. If I were to have that pointer go out of scope, what's going to get destroyed is the A part of the object only, that core, if I don't have the destructors declared as virtual. Because the pointer is only of type A, so at compile time, the only destructor it knows to invoke is the A-type constructor. So whenever we're using classes that have this virtual capability, in most cases, we would like the destructor to be virtual as well, especially if we've dynamically allocated data like in the constructor, like in the example here. We would want the destructor to be virtual so that it would use the right one depending on what the pointer actually points to, so that it would delete the memory. Otherwise, we're back into that, creating orphan memory blocks, and we all know all the bloody details about what happens to orphan memory blocks. And I won't go through that again, but I'm sure some of you are laughing and smiling right now because you've thought of that image that we've discussed several times. So then when we created an instance of that particular type and deleted it, it would call the appropriate constructor and not the wrong one. Okay, not declared virtual, then we're going to end up with memory leaks, orphaned memory blocks, and again, we all know what happens to those. So that's a situation where we would want to use those destructors in a virtual sense. So hopefully this is going to help you in your next homework assignment in terms of being able to create similar functions for like check-in and check-out and that kind of stuff, and other things you need to do with your different types of library items.